and there's going to be an analyst who observes these actions, but not the information. Okay, so Max is taking some actions over time. Jonathan is observing his actions, but Jonathan is not observing what Max is seeing before taking those actions in terms of information. And the question we are interested in, the high-level question we're interested in, is which action sequences Jonathan, sitting on the outside observing these choices, can he rationalize? Okay. Is that a question? Sorry. Okay. So that's the high-level question. One example to keep in mind is this very simple investment example, which I have on the normal form, kind of quotes the normal form on the left-hand side and the extensive form on the right-hand side. So there's a firm. The firm has two choices in the first period. The firm can either invest or not invest. If it doesn't invest, the game ends. If it invests, then it has the opportunity to invest again or pull back the earlier investment. Each round of investment costs 1 unit. And if the project is a success, you get 4 units. So that's why there is a payoff of 2 and minus 2 here. And the payoff produces a positive output only in the good state. Okay, so you see these payoffs, they're in good state and bad state. Okay. This is the simple 2-period decision problem. It's a dynamic decision problem. And what is interesting, to note is that there is an action sequence here, invest and pullback, which does worse than an alternate action sequence in every possible state of the world. That's why I wrote down the normal form separately, right? So you see that even though invest and pullback is giving you a lower payoff in each state of the world, obviously you can rationalize it, right? So the first question, kind of naive question you can ask is, can invest and pullback be rationalized? Yes, of course it can be rationalized. So Jonathan is thinking through this while Max has made this decision, and Jonathan, convinces himself that, well, Max could have seen a signal that the state is very highly likely going to be good. And then he sees a signal that the state is actually not very highly likely to be bad. And so that's why he invests in the first period and pulls back in the second period. A second type of question you can ask yourself is, can it ever be rationalized with probability 1? Can this action sequence, invest and pull back, be rationalized with probability 1? And the answer is going to be no. Okay, precisely because of the reason I just said, that because it's kind of dominated in this particular way. A third question you can ask is, well, okay, if it can be rationalized and it cannot be rationalized with probability 1, there must be some upper bound. Can you precisely tell me what that upper bound is, beyond which Jonathan cannot rationalize this action sequence being taken, given the information? So Jonathan has the information that you see on the slide, okay? He doesn't have any other information. And the answer that we will tell you is that, yes, precisely, Jonathan can precisely pin down that it's only up to 66% that the action sequence can be rationalized. Another way, a kind of decision theoretic way of saying this is that if there's lots of people like Max making this decision with broadly similar kind of situations that they're facing, and if more than 66% of the people end up taking this action sequence, invest and pull back, Jonathan cannot find any rational standard rationalization for that. Does that make sense? That's kind of the questions the model can ask, and we're going to do this very, very generally. Okay.
Just a quick side note. So if I was seeing a large number of people do this, I would have to see more. So I'd have to see conditional on investing. I would have to see them invest at least 2/3 of the time, or is that too strong? Or
conditional on
investing.
No, then you have to Bayesian update. I'm saying ex ante probability. So
you're saying ex ante. Okay.
Yeah,
but I would also have to see if I could see final outcomes, I would have to see conditional on investing expectation non-negative. Right.
I don't really understand what that means. So
I would have to see people who invest doing at least as well as people who don't invest. Right.
Sure. You're making a conditional statement. Sure. Yeah.
Okay.
I'm saying just in this data set, I'm saying you have this entire data set. In this data set, what is the maximal amount in which you can rationalize this action sequence?
Yeah.
You're making a conditional statement. Yeah, I agree with that.
Sure. Okay.
Yeah. Mm-hmm.
Okay.
And just Rohit, just because, since we're asking questions, and if I was to ask the converse question, which is basically, suppose I observe the distribution of actions, can I pin down the payoffs?
So that's a good question. I'll come to that. So for now, I'm going to assume that that you observe these payoffs, and I'll come to actually in the next example, you'll see that I will only make partial assumptions about the payoff, and you can back out some information about the payoffs. You'll need to give me something about payoffs, but I'll come to that. That's a good question. So for now, we're assuming Jonathan knows this slide. Okay, but you're right. So what Rahul is asking is, what if I don't know it's 2? What if I know it's 2 times delta or something like that? Can I know something about delta? And I'll come to that precisely in the next example. Okay, so let me give you the general model. The general model is very, very kind of vanilla, and Henrique and I were kind of, we kept thinking for about a month that somebody, it seems, too classical. So, but David Pierce convinced us that nobody had done this before. So there are T periods, and in each period, you're going to have a set of actions. Everything is going to be finite. There is a finite set of states of the world, and then there is a utility that will be realized as a function of the actions that that Max has taken and the realized state of the world. Okay, so again, sort of in the context of the question that Rahul raised, and I'll come to this. So Jonathan knows this slide. Okay, so this is Max's problem. That he's kind of simple problem. What I do want to underscore quite a bit is that we're making absolutely no assumptions about you. Okay, in particular, it doesn't have to be time separable, which we think is going to be important for a couple of applications and connections we want to think about. Okay. All right, and this is Jonathan's slide. So as we said, Jonathan knows this utility function, and then he sees a sequence of actions being taken. Okay, and then he asks himself, when can invest and pull back, for example, be rationalized, or can it be rationalized? So when can action sequence A be rationalized under some information structure? That's the question Jonathan asks himself. We're good? Okay. So here is just to give you a timeline structure. This is how we're going to model information. It's going to be a very standard sequential information structure. So the state is going to be drawn from some prior. Then the agent is going to see a signal. This is drawn from a prior. Agent sees a signal, takes an action, sees a signal, takes an action, up till some finite time period t. Okay, and then the payoff is realized. All right, so kind of standard, information, action, and then some payoff is realized. That's kind of the general model, and the sequential information structure is what you think it is. Okay, so that's kind of the model. And what are we going to give you? We're going to give you 3 results. Okay, and they're all in the same flavor, but they're going to have different levels of requirements of data from Jonathan or the outside analyst. Okay, so what we're going to do is we're going to give you kind of a tight characterization of what we call rationalizing dynamic choices via dominance arguments, okay, which will make it clear what that means, for 3 types of data. So the example that I asked, in the example itself that I showed you, we could have asked the question, can invest and pull back be rationalized? That would be the first bullet point here. Can you just simply rationalize this? Can a rationalization ever take this action sequence? A second type of question that we asked, which we had a discussion about, was, can you, here is a distribution of people taking actions. There were 3 possible action sequences. Can you rationalize this distribution? Can this distribution ever be rationalized by people like Max, many people like Max who are making this decision? And the third question we will ask is, in addition to the action sequences, what if you also observe the realized states of the world? So the second one is a marginal distribution on actions and states, and the third one is a joint distributions on action and states. So this is even more information that we're giving Jonathan. And then we ask, can Jonathan rationalize this joint distribution? And the main kind of what we think conceptual, technical, whatever you may want to call it, the contribution of this paper is that we kind of unify a conceptual framework to attacking these problems through what we call a deviation rule. Okay, so when I introduce this, you'll see this is a concept that we think is very useful. That will kind of unify all the 3 theorems and proofs of all these results. Okay, so the deviation is going to define the dominance arguments, which is then going to give us a duality result for each of these data requirements. Any questions about the model or the high-level results? Okay, so before I jump into the further description of the model and the results, let me make a few connections. Okay, because I think because the problem is slightly classical, it kind of fits into various strands of the literature. So here is kind of
sorry, Rohit, can I interrupt you for a second? Ask a question.
Yes.
So, let me ask you a cheap question that's typical in these sort of like rationalization. So, what should I suppose that you guys, you want me to take this seriously from an empirical perspective? Suppose you do rationalize and you don't rationalize. What do I learn in some sense as the analyst from that answer? So if, for example, if you reject the data, should I learn from this as that agents are not Bayesian, and what do I do with that information?
Very good. I think our careful approach would be to be slightly agnostic. So our role ends at. So I'll show you these behavioral applications that we have developed. So where we will argue that our role here is to give you a machinery to robustly reject the standard model in the realm of the question that you're asking. Okay. Beyond that, if you think they're hyperbolic discounting, they're time inconsistent, whatever it is, you can go ahead, use that data more in a more sophisticated way and make your inference. What we are going to give you, which I think is very useful even for the behavioral literature, is a clean, robust way in a very general set of models, time inseparable and so on, to reject the model. So I'm not going to take a very strong stand on what you would want to do with that information. Our role as a modeler is to give you that methodology. Is that okay?
Yep, thanks.
Yeah. I mean, I can say more. This is something compact. This is I can say for sure, and you can go home with it without any worries. Other questions? Okay, so the connection zero, and there's a reason zero, we're calling it in the sense that it's kind of a basic role of this model is to do what kind of, from Kahneman to Tversky's time, we call, characterizing the empirical content of the model. So what do we mean by that? So at a high level, you're trying to write down some model to rationalize either a data set or to predict some behavior, or to rationalize some choices. You take some call on preferences, you take some call on how you're going to model information, and then you make some call on behavior. For example, this person is an expected utility maximizer, or this person is a Bayesian, and so on. And then you can rationalize. You can have some predictive content of the model, right? You can rationalize some choices. So what we're going to do, and this again comes back to Rahul's question, is we're going to take no stand at all on information. So that information is going to be completely we're going to agnostic. We're going to take some stand on preferences, and I'll tell you what I mean by some stand. And we're going to take some stand on behavior. So even though I want to delay this discussion if you have any questions, even though we're going to assume throughout the talk that the person is Bayesian, but it's not really necessary. And Rahul in one of his papers actually points it out very clearly that for these class of models, you can make much weaker assumptions in behavior. So our role here really is to have make some assumptions on preferences, some assumptions on behavior, no assumptions in information, and then try to provide an empirical content of the model to have some prediction on choices, on choice data. This contrasts slightly with or fundamentally in some sense with the stochastic choice literature, which makes weaker assumption on this diagram that I have on the left, in the sense that it makes less restrictive assumptions on preferences, less restrictive, similar assumptions to us on information, that is that they don't make strong assumptions in information. And so in that sense, they produce starker predictions, but nothing in life comes free. So they also have to make very, very strong data requirements. In particular, you end up making assumptions about comparing menus of choices with menus of choices in the world of all possible menus of choices and so on. Okay, so high-level message is they have, they would make stronger predictions in axiomatic language, but they require much stronger data. For example, in our model, as you already saw, you can predict something even with one action sequence. You can say whether you can have the model can have empirical content even with such minimal data. Okay, so I would say these are complementary but distinct perspectives on characterizing the empirical content of a decision problem. Okay. And there's, this literature is large and growing, and in particular, it has very cool applications to I/O and many other applied problems. And we are hoping that this different perspective can also shed light on a lot of these applied problems. Okay, second connection is with standard rationalizability that we learn in undergrad now, I guess, if not grad school. And you would remember that all of us did this very classical result in game theory due to Wald and Pierce. In a static kind of two-player game, you can say an action is rationalized if it is the best response to some belief about the other player. Okay, and the result that we have in textbooks is that an action is never a best response if and only if it is dominated by a mixed strategy. So I want you to remember this, both this result and the style of result, because I will be invoking this when we show our theorems. Okay, this is kind of what I want you to have in mind. And once you have this result, you can do very cool things. In particular, Jonathan and Batigali et al. Have these recent papers, where they show something which is kind of very elegant, and it's kind of surprising that that it hadn't been thought of before. They use this theorem to show actually that the set of rationalizable outcome expands in the level of risk aversion of the agent. Okay, and using our methodologies, we will be able to extend this result to a dynamic model. Okay, so this is kind of just, if t is equal to 1 in our model, you'll get some result like this. But what happens for t greater than 1 is what this paper is about. Okay, second connection is with behavioral economics, and this is, Rahul, where your question kind of comes in. There's some very prominent papers in behavioral economics that have, rightfully have lots of citations, and I have been very prominent in thinking about dynamic decision problems and seemingly mistakes that people are making. Okay, so where we will come into this, you may remember this gym contract paper by Delavinia and Mamadar, where they show that people pay large amounts of money upfront to sign for gym membership, but then don't go to the gym that often. Or Michael Grubb has this paper which shows that people sign up for very low minutes of data and minutes, contracts with very low amounts of data and minutes on the cell phone, but they end up overusing it. There's another stuff on credit cards and so on. So there are lots of these dynamic decision problems where people act in some kind of dominated way. But where we come into the picture is that we argue that there is, even though there are lots of these studies, there is no kind of general unified model that you can write down. And we would emphasize that actually even some of the models that have been written down assume time separability, which we don't think is a very good assumption for some of these models. For example, if you're going to the gym, you have a target health status in mind. If you're using phone contracts, you have some target amount of phone minutes that you want to use. If you're using a credit card, you have some credit limit in your mind, and these are inherently non-separable. Okay, so what we are offering is a very general framework, and I'll come to this later in the talk, which, answering Rahul's question, will allow you to reject this model robustly. After that, whether you want to rationalize it using hyperbolic discounting and stuff is outside the realm of this paper. But what we will tell you as a behavioral economist is, if you're interested in analyzing this data set, here is a way to robustly reject the standard model. Okay. All right. And quickly, so, as you can see, I just modified the investment example into what looks very similar to this popular paper by Jeff Eli and Martin, Sadowski, which is called Moving the Goalposts. And again, here, the way, from what I remember, Jeff motivating this in his talk is that you want to motivate a student to attack a hard problem, but if the student knew at the outset the problem is very hard, they would never start on the problem. Right. So how do you motivate someone to take the action effort? No static information structure can motivate the agent to take the action effort in the first period. But what they say is you can use information as a carrot to rationalize taking effort in the first period. There's also new work by Weiji Zhong and Ben Herbert, which argues, when can I convince you to be on a platform like Facebook or Twitter, even though you may know that in the long run it may harm you? So I give you incremental pieces of information. So to all these general kind of approaches, so to all these sort of specific questions of dynamic information design, we provide, again, an alternate way to think about it using deviation rules in a very general way. Again, because of non-separability of utility and our general framework, what we propose to these models is a very general way of looking at some of these dynamic information design problems. And finally, and this, I'll come to Rahul's question. What Rahul was asking was, is there any way of eliciting preferences as well in addition to information? So what we can do, and I'll show you an example after this, is to parameterize the utility function with some parameter delta. And I don't know delta. You have to give me something on a utility, so I parameterize it, and then what I can do is, depending on the data assumption that you have, data regime 1, 2, or 3, I can back out information about delta. And what is interesting here is that it doesn't make any assumptions on information. So I can still get some traction out of the model in terms of the empirical content, both in terms of backing out some utility and predicting choice behavior without making any assumptions on information. Okay, so these were the 4 connections. Now let me come to stating the results. So I'm going to define a strategy, what it means for an action sequence to be rationalized, and then dominance. And then I'll give you the result. So strategy is something that you would think it is. So remember, there was an information structure, and after seeing the signal, so S is a cardinal, is the product of all signals, you take an action. Right. So a strategy, in the first period, you see signal S1, you take an action A1. In the second period, as a function of the signals, signal 1, signal 2, and the action that you've taken, you take another action, and so on. So in a compact way, a strategy is simply a mapping from the set of all set of all adapted mappings from the set of signals to the set of actions. And adaptedness here simply means that the marginal distribution on the first T actions is only a function of the first T signals. Okay, so I haven't observed the signals in the future, so my actions cannot depend on the signals of the future. My actions today can only depend on the signals that I've realized till today. Make sense? Okay, so that's just what adaptedness means. This is kind of the full definition of a strategy. Okay. So now a sequential information structure and a strategy together would produce a distribution over action sequences. So you can see here, this is you're going from set of states into set of signals. This is the mapping pi, and then depending on the realized signal, you're going to go to a distribution of actions, which is your mapping sigma. So this is the composition mapping that is going to produce a distribution over action sequences. Okay. The agent's problem is then given some prior P. So there is some prior, let's say P, and some sequential information structure pi. The agent is simply going to maximize their expected utility given in best responding to this information structure. Okay, remember that's the timeline that I showed you: signal, action, so on. So agent is just best responding to the information that she's receiving and trying to maximize her expected utility. Make sense? Okay. So what do we mean by rationalization? I mean, it kind of intuitively already makes sense, but let me formally define it. We will say an action sequence A is rationalized by a triple sigma pi P if the agent is best responding to the information structure, and in best responding to the information structure, the action sequence A is chosen with positive probability. You see, it's a very minimalistic definition, right? The only thing I'm requiring is that when Max is making his choices, he must choose this particular action sequence in best responding to whatever information structure he's facing with positive probability. Okay, so Max only has to satisfy 2 conditions. He's best responding to some information structure, P and pi, and within that best response, the action sequence A is being chosen with positive probability. Okay. All right. So let me give you an example to think about how we're thinking about this. So here is an example which we call the waiting game example. So you can either wait in the first period or you can take actions X and Y. If you wait in the first period, then you can get to choose actions X and Y again in the second period. Okay, and the payoffs are given. So, and their states capital X and capital Y, and your goal is to match the state correctly. So if you match the state correctly, you get a payoff of 5. If you don't match the state correctly, you get a payoff of 3. And if you wait, then the same problem, the same situation arises. Is just that you lose some value delta because of waiting. Okay, so this is a matching the state game. You can have, if you match the state correctly, you get a payoff of 5. If you don't match the state correctly, you get a payoff of 3. And if you wait, the same problem, it's the same replica of the problem, but you lose a payoff delta because of waiting. Make sense? So the question I ask is, well, you know, can weighting be rationalized, and for what values of delta can weighting be rationalized? Okay, so one thing should be immediately clear, just that looking at the payoffs, is that if delta is less than 3/5, weighting cannot be rationalized. Why is that? Because the worst thing you can get is 3 delta. The best thing you can get from weighting is 5 delta, and the worst thing you can get from not weighting is 3. So if delta is less than 3/5, you should never weight. The question is this an if and only if statement? And obviously it's not. That's why this example is interesting. So the question is, what is the tightest definition that the tight statement that you can have is when is it optimal to weight? Does that make sense? Okay. So here the set of states of the world, to put this in the language of our model, the set of states of the world are capital X and capital Y. In the first period, you have 3 actions, X, Y, and W. And then in the second period, you have 2 actions, X and Y. Okay. Here is a simple signal structure that will, that I want to kind of put on this model to see what it spits out. Okay. So suppose you get no information in the first period, and then you get precise information in the second period. Make sense? So no information in the first period, and then precise information in the second period. So the agent's best response is obvious. If it sees the signal SX, it should play X. If it sees the signal XY, she should play Y, because you're getting full information. This is the agent's best response. Okay. Let's assume there's a prior 50-50. Okay. Then without weighting, the payoff is 4. Remember, because I said the prior is 50-50, so you take just the average over this half, right? So you get a payoff of 4. But if you wait, you get a payoff of 5 delta. Why 5 delta? Because I have precise information in the second period. And so I'm able to get 5 delta for sure. And so clearly in this information structure, you should always wait as long as delta is greater than 4/5. Okay, I just constructed a very simple information structure for you to show that when delta is greater than 4/5, you can rationalize weighting. But the harder part is now to show, so you can already see that the if and only if statement will be, you should wait as long as delta is greater than 4/5. The much harder part is to show if delta is less than 4/5, what happens? Okay, because you have to now go through all possible information structures. Right? So instead, I'm going to construct a deviation to show you if delta is less than 4/5, you shouldn't wait. I hope this is clear. It's right. So if delta is greater than 4/5, I just constructed an information structure for you to show that it is possible to rationalize weighting. Now, showing that if delta is less than 4/5, it is not possible to rationalize weighting is a very hard thing in the space of signal structures, because there is a for all there. For all signal structures, this must not be true. So I'm going to replace the for all for there exists. Okay. So how will I do that? So suppose delta is less than 4/5 and you're still waiting. Okay. So max, we know that delta is less than 4/5 and somehow max is still playing wait. So Jonathan looks at this action at this choice data and tells Max to do the following. He says, Max, I don't know what information you're observing, but why don't you do this instead? Right? If you were taking X, keep taking X. If you were taking Y in the first period, keep taking Y. But if you were taking W in the first period, switch to a half-half randomization between X and Y. This is Jonathan's recommendation to Max without knowing anything, any of the signals that he's observing. What this does is it gives Max, it allows Max to do uniformly better, irrespective of whatever information he was observing. Okay, this is what is a deviation argument, because and it's not sensitive to the information structure at all. Okay, so if delta is less than 4/5, then this particular strategy, this particular deviation strategy that Jonathan is suggesting to Max is going to help him do uniformly better, no matter what state of the world realizes and no matter what information he's observing. Yeah, somebody had a question. Yeah.
Yeah, I have a question, Rohit. I mean, this is a feature of this particular example and the way you guys constructed payoffs.
Yeah.
But in this particular example, like, it's much easier to just say that, you know, having no information in the first period is the worst possible state that you could be in the first period, right? So you could just use that to pin down the 4/5.
Yes.
And so in this specific example, you could do something that's potentially simpler than what Jonathan is suggesting.
Yes.
But that's the feature of the fact that the payoffs are dominated in this way.
Right. So fair point. So the two ways to think about this: we are, in terms of applications, we are particularly interested in these kinds of payoffs which are dominated in this way because they seem like mistakes. So even here you see that notion X always gives you a higher payoff than WX, no matter the state of the world, right? So it seems kind of ex post, it might seem like a mistake, but it's really not, right? So in that sense, the point is taken, but we actually are interested, even though the theorem is going to be very general. The second point is yes, in a more when I show you the more general theorem, I'll come back to this. Is that yes, the way we propose to use our sort of technique is precisely to come up with a signal structure and a deviation rule, right? Because it's an if and only if statement, right? So at one level. So what deviations rule will help you do is it makes sense of the problem even when you're not being able to come up with any signal structures. So any one deviation rule will help down the class of possibilities. And then once you have a reasonable grip over some things that can definitely not be rationalized, you can then look for a signal structure because it will just become easier to do so. So I'm not saying that this will solve all problems. What I'm saying is these two techniques together will help you give an if and only if statement. Henrique, do you want to say something? Okay. Okay. All right. So let me now try to push this argument a bit further. I hope this is clear why Max is able to do better because he gets a payoff of 4, irrespective of, so whatever P may be, he gets a payoff of 4 by doing 50-50 between X and Y. Okay, so if delta is less than 4/5, he should just not wait. Okay, and this also partially answers Rahul's question about here we are not assuming that U is completely known. Jonathan knows this matrix, but he doesn't know delta, right? So you're still able to partially identify what delta should be through using this theorem. So rephrase it. If Max does indeed take the action weighting, and if we assume he's rational, then we can conclude that delta must be greater than 4/5. Okay. Okay, so what's a deviation in general? So what we just proposed was a deviation rule. A deviation rule is going to be a function from actions to lotteries over actions, which is adapted. That's it. Okay, so deviation rule, it's a set of recommendations. So this is Jonathan telling Max, I observe what you're doing. Why don't you do something else? And I'm going to tell you precisely how. The only restriction we're going to put in this mapping, again, is that it's adapted. And even though it looks simple, it actually packs in a lot of punch in the sense that all complexity of dynamics is going to be packed into this adaptedness assumption. So you'll see that when you look at the statements, they seemingly look like they're meant for a static model, but actually they work very generally for dynamic models, and the only thing that is driving the dynamics is this adaptiveness assumption. Okay, so what's it? Well, again, the adaptiveness simply means that in the first period, Jonathan can recommend Max a deviation that only depends on Jonathan's first period action. Then in the second period, he can only recommend a deviation that depends on his first and second period action and the deviation that he's recommended in the first period, and so on. Okay, that's the definition of a deviation rule. A mapping from actions to lotteries over actions such that it's adapted. So you'll see through our examples that this is actually has a lot of bite. So you might, let's go back to the weighting example. So Jonathan might be tempted to tell Max to do the following. If you were doing X, keep doing X. So this is this arrow here. If you were doing Y, keep doing Y. But he'll say, well, if you were doing WX, shift to X. And if you were doing WY, shift to Y. This seems like kind of a nice recommendation, but it's not adapted. Why is it not adapted? Is because Jonathan is using second period information to recommend first period deviation. Right? But the moment he says move WX to X, he's using the fact that you're going to do WX to move in the first period. So if he's recommending you to move from WX to X, he has to recommend WY also move to X. That's what adaptiveness does. Okay? I hope this is clear. This is kind of the most important conceptual part. So adaptiveness is saying you cannot use future actions to make deviation recommendations today. If WX has to move to X, then WY also has to move to X. So the deviation that we recommended actually was the one that said move both WX and WY to half of X plus half of Y. So both these move to this particular deviation. This is adapted. Make sense? Okay. Once I have this definition, I can now define a notion of dominance that we were implicitly using in the examples. Okay. So an action sequence A is truly dominated if there exists a deviation rule such that it weakly improves upon all action sequences and it strictly improves upon the action sequence that you're seeking to dominate. Okay, both points are important. So in particular, you might be tempted to think that only two is necessary, right? That, well, I want to dominate action sequence A, let me just do a deviation such that I improve the payoff upon A. But because of the adaptiveness restriction, it might make you move from some other branch as well that you don't want to move. And so you just cannot simply put the identity mapping here. You cannot just say, well, don't move on any other branches. This is a very strong notion of dominance. It's saying, well, the action sequence that you think is giving you a bad payoff, let's move away from that and get a strictly higher payoff. But in the process of doing so, you should not make anything else worse off. Does that make sense? So why let's go back to the investment example. Why can't I do this in the investment example? So this is not invest. This is invest, pull back. Why everything can be rationalized in this example is because if I move invest and pull back to not invest, then I also have to move invest and invest to not invest. Okay? And this will violate condition 1. Because this is 2 minus 2 and 0, 0. So this payoff of 2 is less than 0. So there exists some B, some other action sequence that is becoming worse off because of the fact that you move the one that you think is being dominated. So when you move something, nothing else should also become worse off. Okay? And then the main result is what you would expect, that a sequence of actions can be rationalized if and only if, cannot be rationalized if and only if it is truly dominated. Okay, so the two definitions I gave you, one of being rationalized, the other of being truly dominated, are equivalent in a very general class of models. Okay, so you can see kind of that this is a generalization of what I showed you for t is equal to 1. Questions?
Can I continue to abuse my panelists?
Yes.
Yeah. So I think, and I apologize, my cat might yell in the background, but basically, this is a very elegant result. But if we go back to this discussion about the gym memberships and using this in practice, if I want to figure out if something is truly dominated, I apologize. Oh, sorry, I'm just going to smack my cat. If I want to figure out if something is truly dominated, like in practice, is this very hard to do? Like, is this a linear program or something?
So yeah, it is exactly. It's a linear program, exactly. So I'll come to precisely the gym membership thing. We have a new result that kind of shows you in all those class of models what would this reduce to. So for that, I need to do what they do is they do all their analysis on distributions. Right, so I'll come to the distribution result, and then we can go back to this. But exactly, yeah, it's using the data sets is actually fairly easy to do.
Perfect, thank you.
I'll come to that precise question. Okay, so first immediate application that you can do is, remember I told you about this very elegant result that Jonathan and Pierre Parlo et al. Have. You can I won't go into the details, but you can generalize this result now to the dynamic model using very similar techniques to what they do, but using the idea of deviation rules here. So one of these inequalities is Jensen's, the other is a deviation rule. And our pitch is that if you did not use our result, we wouldn't know how to prove this result, even though it's very elegant and the proof is straightforward once you know our theorem. If you were only in the space of signal structures, we wouldn't know how to prove it. So the result says that the set of actions which can be rationalized increases with risk aversion. So if Max gets more and more risk averse, Jonathan can rationalize more and more action sequences. And to prove this result, we're using theorem 1 that I just showed you. So I don't have time, so I'm not going to go to the details of the proof, but it's fairly straightforward once you understand what deviation rules are. Okay. Now let me, in order to answer Rahul's question, let me increase the data requirement now. Okay. So let me go all the way to the extreme, where I say, suppose now Jonathan observes a joint distribution of a population of agents like Max over both actions and states. Okay, then the notation is not important. The definition says, what you think it should say is that the strategy should be best responding to this. So there should exist some sequential information structure in prior, such that the strategy is the best response to that information, and the joint distribution is replicated by the joint distribution produced by the strategy in the information structure. Remember, I told you that the strategy in the information structure produces a joint distributions on actions and states. So give me some sequential information structure in prior. That's your information. Assume that all the agents like Max are best responding to this information structure. And then some joint distribution is produced over actions and states, and that should match the distribution you're trying to rationalize. Okay, this is kind of standard. This is what you would expect the definition to be. And then if this happens, then we say that this joint distribution is rationalized. Okay, now we need to come up with an if and only if result for joint distributions. So obviously our notion of dominance needs to change. In fact, the notion of dominance needs to become much weaker, because this is a much more permissive criteria of rationalization, a much more general criteria of rationalization. So we're going to define something called domination on average. Very simple. A joint distribution is dominated on average if there exists a deviation rule such that on average, the deviation rule gives you a higher payoff than the action sequence, than the joint distribution. Okay, so it's similar. Jonathan is going to recommend the population to instead move to this deviation rule. So he still doesn't know what information they're observing, but he says, well, if you shift to this deviation rule, then on average, all of you are going to do better. Okay. And then boom, we get the result that a joint distribution cannot be rationalized if and only if it is dominated on average. Okay. Now, when we got this result, both Henrique and I were a little, if I can say, dissatisfied. And our dissatisfaction was that if this question hasn't already come to your mind, it really should, is that it's a very strong assumption to assume that not only is Jonathan seeing the actions that the population is taking, but also whether for them the state was realized was good or bad. Right. So for us, a more reasonable data requirement would be to only observe the marginals on actions. So we don't know what happened. Why did Max not go to the gym? Why didn't Rahul overuse his phone minutes? But we saw that they did. Okay. So for us, this seems like a more natural data requirement. So we really like this result the most, and we're going to use this result to attack various applications. So we're going to say Jonathan only observes the marginals on action sequences in the population. And then again, there's a similar definition of rationalization. There exists a sequential information structure and prior such that all the agents best respond to this information structure, and the marginal of this joint distribution is replicated in the data set that Jonathan is observing. Okay, so when now all of you make this decision to go to the gym or not, we only observe as an analyst whether you made those what decisions you made. We take a distribution over them, and we say that this distribution is rationalized only if it matches in best responding to this. When you generate a distribution over choices of going to the gym, does that match the distribution we are trying to rationalize? But again, we're making no assumptions on information. We're saying there exists some information structure to be consistent with which you must be best responding, and the distribution that we're trying to rationalize is replicated by this triple. Okay. So now, because our notion of rationalization is kind of intermediate, it's neither the first one or the third one, our notion of dominance also needs to be intermediate. Okay, and we're going to call this intermediately dominated. So what do we mean by that? The exact structure is very similar to the average notion, but then the average notion needs to hold state-wise across actions. So you'll see the main difference between what average dominance and this is this minimum function here. Okay, so again, the exact structure is not important. Conceptually, what we want you to take away is that there is some intermediate notion of dominance that we precisely are able to pin down, which is weaker than true dominance, but stronger than average dominance. That gives you the precise characterization for rationalizing a marginal. Okay, so again, here, look, there is no assumptions or information. The only thing you have here is knowledge of preferences. And the result, which is our favorite result in terms of the one on populations, is that a marginal distribution cannot be rationalized if and only if it is intermediately dominated. Okay. This is going to help Jonathan to ask the question whether in a population something can be rationalized or not in terms of aggregate numbers, right? So let me just make a brief comment on the data. I suspect this is kind of on the lines of what Jonathan was asking us earlier. It may look like results 2 and 3 are stronger, which they are, obviously, because they're giving you so in some sense you can think of theorem 1 as a statement on the support of things that can be rationalized, and theorems 2 and 3 a statement on the shape of things that can be rationalized. But obviously they make stronger assumptions. So in the background, as we see in stochastic choice literature, there is this assumptions lurking that we're making an assumption that all people who are making these decisions are almost exactly like Max, in the sense that they have the same utility function, they're getting signals independently and so on. So for example, if there was correlation in the signals that Rahul and Max were observing, then this theorem doesn't go through as is. Right, then the best thing I can say is, well, theorem 1 is valid. So in that sense, we really like theorem 1 because it's a very robust conclusion. And you should think of theorem 3 as being a very strong result, but depending on certain assumptions on how you interpret the data. Okay, now I don't think I have time to go into the proof sketch, but but a critical step is to rephrase the obedience principle in the language of deviation rules and come up with this kind of dynamic notion of obedience. Okay, so I'll come back to this if I have time, but I do want to get to the applications. So here is one way of using these set of results along the lines of what Rahul was saying. So to that end, I'm going to define a notion of apparent dominance. Okay, and this is, Rahul, exactly what you were thinking, was that if an action sequence is dominated by another alternate action sequence or a lotteries over action sequence for every possible state of the world, then it's apparently dominated. It looks like a mistake. Why did you pay upfront to the gym and not go to the gym? Ex post, it looks completely dominated. Right? But obviously it can be rationalized, as we saw in the moving the goalpost example or the invest example, that even something that looks dominated can be rationalized through a dynamic information structure. So for example, now in the weighting example, you can ask the question, when can you rationalize weighting? And now what we can do is we can tell you, or we can ask a more precise question, is what is the maximal probability with which you can rationalize weighting? Okay, now I'm going a step further. I'm using theorem 3. So you observe a data set of people making the weighting decision or not making the weighting decision. What is the maximal fraction of people that you can rationalize weighting as a function of delta? If delta is 1, then you can rationalize everyone weighting. If delta is less than 4/5, then you cannot rationalize anyone weighting. And in between, you have this, it doesn't look, but it's a concave function, and we can precisely pin it down. And this is the functional form. And in a graph, we have shown this. So in the weighting example, Jonathan can ask the question, if people like Max are making these decisions, what is the highest level, what is the highest fraction of these people that I can rationalize a function of delta? It will, for delta greater than half, it will always be between 50% and 100%. So as delta gets larger, more and more, he can rationalize more and more people weighting. Okay. So in that sense, theorem 3 is very powerful. It allows Jonathan to make very strong conclusions about rejecting or accepting the standard model. So now let me come to this question that was raised about the behavioral models. So here is a model we propose. We say, let's assume quasi-linearity, okay, which is something all these models assume, but we are not making any other assumptions. In particular, and I would like to emphasize this again, is that we're not making assumptions of separability, because we actually think in a lot of these models, targeting objectives is very important, and targeting objectives is inherently non-separable. Okay, and here is, let's assume that A0 is the choice of contract, whether it's the gym membership or the phone contract, and then A1 to A80 is your usage. Okay, then basically this falls within the structure of theorem 3, and we assume that Jonathan is now observing data set on people, either going to the gym in Boston or using phone contracts and so on, and we have a precise result which says that suppose the agent chooses a contract A0 and uses the service through actions A1 to A80. This is how many times you went to the gym, for example. And Jonathan observes this distribution in the population in Boston, which is where the paper was based. And this distribution cannot be rationalized if I can come up with an alternate contract. For example, instead of paying upfront, you do pay as you go, such that on average, the population does better.
So Rohit, you should explain that M is the amount of money that you're paying, right?
Sorry,
so this is how.
Yeah, go ahead.
Yeah, so in the case of the gym membership, this is exactly how much you pay for your gym membership, and in the case of the cell phone contract, how much you pay for the cell phone contract, including everything, right? So if you, let's say, sign up for a contract that allows you low usage and ends up overusing, the M includes all the fines that you have to pay, everything. So all we're assuming is that you have a utility for how much you use this service, and that's separate from your utility for the money that you have to pay, right? So this doesn't interact.
And you see that eventually in the result, the V doesn't even function, right? The feature, right? The V gets canceled out, and the result is only in terms of aggregate payments. And again, in a very general way, you can reject the model. So if I observe a data set that doesn't seem, to comply with the standard model, here is a robust, clear way of rejecting the standard model. Okay, and in fact, what both these papers that we cited are doing, they're doing something like exactly like this. They're constructing deviation arguments, but they're not formalizing it like that. So in fact, if you look at the Delavinia paper, they actually say something to that extent. They say if the consumer switches to pay-per-use contract without changing the attendance, so A1 to A2 doesn't change, but A0 changes, then she will have a higher utility. And they implicitly are assuming higher utility on average. Grubb precisely says this. Grubb says that the fact that on average Plan 1 customers could have saved money had they all chosen Plan 0 provides evidence that consumers have ex-ante bias belief. So he interprets it differently. But the result is both of them are actually implicitly precisely using this result. Okay, and we can go into the details towards the end, to sort of kind of show you in a more compact way. I just put in the quotes, but you can actually show formally that their kind of setups will be subsumed by our this very simple model.
We have time for a question, organizers. Yeah. Or we can wait because we're almost okay. But I have a question about this. Like Rohit, this is a very striking result. Would it be correct to say in this result that essentially, let's take the gym membership example. Yep. You're basically saying that if I cannot explain, because the V's drop out, right? So you're basically saying that if I cannot explain someone's behavior as a standard discounter,
yeah,
also cannot explain their behavior as a hyperbolic discounter. So in other words, if I'm looking at a class of models where, let's say, I just think of somebody as having, some sort of time discounted preferences, essentially what you're telling me is that somehow these sort of behavioral models of discounting have no added explanatory power over just like standard exponential discounting?
That's a good question. We haven't thought about that. So it definitely rejects the standard model. So you're saying over and above that, are we also rejecting?
Because the V's don't seem to matter, right? So you're basically sort of saying that if you know what the contracts people have, then essentially I can somehow this is ruling out all kinds of behavioral preferences that I would normally appeal to if I was trying to explain gym behavior.
No, that's a fair question. I haven't thought about that. Henrique, that's a stronger claim that we are making, but he seems to be right.
Yeah, I'm not sure because we are assuming time consistency throughout, right? So this M is kind of like implicitly, when you think of discounting, for example, M would be like the expected present value, right? It would be the present value that you have after you include all the discounting for the money that you pay, the stream of payments that you do. But if you have a hyperbolic discounting, then I guess that it
can't be sophisticated. Maybe it's sophisticated versus naive. Like maybe sophisticated hyperbolic discounter follows what Rahul said and has no additional explanatory power, but naive would.
Right. Right. Exactly. Yeah, that's what I was thinking. Right. The naive, I think, would be kind of a different thing.
Yeah, that's a very good point, actually. Thanks, guys. Yeah, that's a very good point. Yeah. So I guess what Henrique is saying is that implicit in both, and I'll just wrap this up, Max, after this. So implicit in both V and M, we are making an assumption throughout that you're time consistent, and because M, when you unpack M, it's as if whatever you may write, it has to be time consistent. But I think both of you are making a very good point that it may work for the sophisticated, but not the naive. We'll think about that. But thanks. That's a very good comment. Yeah. Yeah. So this is a new addition in terms of applications, and yeah, we have two other applications in the paper. This I already showed you through connections to the literature that it connects to a bunch of things, and we have ideas on how to take this further, which we're happy to talk about. And since I'm out of time, I should wrap up and be around, and we're happy to take questions.
Thank you. This was excellent. So we are at the end of the talk itself, but now we have about 15 minutes, maybe slightly less, of questions and answers. We're still recording, but we, as is usually our custom, we would start with the panelists. If there are any sort of last moment questions or comments, I don't know, maybe Rahul, you'd like to start, and then we'll move to Jonathan.
I have questions, but I've been monopolizing the questions. So I'm going to let Jonathan go first because I've been talking way too much. So Jonathan, you go first, and then I'll chime in with my hot takes.
Yeah. So one thing I was speculating on was, so we could think about applying standard rationalizability results to normal form of this game. Now, because you don't pin down an equilibrium structure, we'd be doing that over a set of normal forms, right? And we'd be asking whether something is rationalizable in any of those, whether any of those normal forms have a rationalizable strategy that shows us the path of play that we observed with positive probability. And does that, so I was thinking of that like before you started showing your proof. It appears that your proof doesn't approach it that way. I'm wondering, like, if you do approach it that way, like, do you get anywhere?
So two comments.
Yeah.
One, that, you know, so even though we are invoking kind of the structure of rationalizability, ours is fundamentally a decision problem.
Yeah, sure.
Okay?
Sure, like the one person version, the Pierce-Wald lemma. Yeah.
Right, exactly. So it is, so that's one. The second is that, so yeah, you are right. We kind of do reduce the game to, if you may, a static form, let's say. I won't use the normal form, and deviation rules help you do that, like, so, because all dynamics gets embedded in the adaptiveness assumption. And the proof kind of uses, you know, so this is the proof of the static result, right? If something is never a best response, if you know, if this condition holds, right, and if something is dominated on average, if this condition holds, and then you kind of have this equivalence using the min-max theorem. Now, in our general form, we try to reduce the problem so that something like that can be applied, which you see here. So we go from, you know, this infimum over information structures and maximum over strategies. And then from going from here to here, we use the obedience principle because we're replacing the strategies with joint distributions and replacing the information structure with joint distributions and strategies with deviation rules. But then the standard flip of quantifiers is not easy to do. There are 2 or 3 problems which we can go into later. Okay. And so we kind of rely on this kind of a Motzkin transportation theorem or a generalized separation lemma to flip the order of quantifiers.
Okay.
And then once you flip the order of quantifiers, then yes, then it's a similar approach.
Okay. Okay. Yes.
But what we like to emphasize is that you're able to again use these techniques because of, you know, conceptualization of this as deviation rules and then using the obedience principle and so on.
Okay, thanks.
Okay, I've been dignified. Let me. Can I just revisit this? I'm very struck by this like V and M result and this discussion that you know we just had with Jonathan. So in principle, if I was thinking about, let's say, a guy who, you know, was a naive hyperbolic discounter, or somebody basically whose preferences may not be consistent over time, right? In sense, can't I just apply your test? I applied once at time 1, and I apply it again at time 2, again corresponding to different preferences from a different starting point, applied period by period. If I wanted to, because the V's fall out at some level, like, you know, maybe I have a different V in period 2, but it doesn't really matter because I can just start your test from period 2 and so on. Am I making any sense?
Yeah, but at time 1, if I don't have rational expectations about how much gym usage I'm going to have, then everything's sort of out the window, right? Because the thing that can happen with naivete that can't happen with sophistication is that the whole population can have the wrong expected value for their gym usage. Like that they all think they're going to go to the gym a lot, and then they don't, right?
Yep.
Right.
But there is, I mean, yeah, I mean, one problem with Rahul, what you're proposing is that A is kind of sunk, right? So at the start, A0 is you paid it.
But I still do stuff after.
But technically what you're saying is still valid, but yeah.
I mean, I'm not saying the condition will look like this. I'm just basically saying that, like, the version of that you guys can.
You're saying, another way to put, I guess what you're saying is there'll just be a larger set of constraints, but there should be some mapping. There potentially could be some mapping between that lot, because you're doing this every period now. But I think I have to think about what Jonathan is saying also. Yeah, Henrique, you want to chime in?
Yeah, I think Jonathan's point is correct. I mean, basically, just to use this example, right? Like you could, I pay for the gym today because I really expect that I will go to the gym a lot, right? And so if your expectations are wrong, you can rationalize something that you would not be able to rationalize, with a standard time consistent model. So I think there is a larger predictive, power, if you can say it like that. The set of allowed things is larger if you allow for a naive, hyperbolic discounting set.
I mean, the set of possible paths might be the same, but it seems like the set of distributions, the distributions over paths will be more permissive. I mean, because without naivete, we can see some person making choices that are ex post wrong, but you can't see a population average that's ex ante wrong. But with the naivete, people can be ex ante wrong.
Yes. Okay. Sorry, go ahead.
I was thinking, just even with the sophistication, now I'm thinking, it could be that you restrict yourself to, so that you have a preference for commitment, right? Possibly. So you could restrict yourself to something, to an action sequence that is truly dominated.
Oh yeah.
But because you think that, later on, if you try to deviate to whatever dominates it, later on you would, not follow this deviation through and actually do something that would make it worse.
Yeah, that's
so I think even even then you could have things that are truly dominated. I'm guessing, right? It's something you need to think a little bit more carefully, but
that
sounds like it would be possible.
That's right. Yeah. So for a different reason, sophisticated people can do things you couldn't see otherwise, because they're using commitment devices. Yeah.
And let me just say one last thing. Sorry, and Max, I can stop talking now if you want to open it to the floor. But okay, one question about the framework, right? And maybe this might not be sensible at all. Is in some sense in this framework you're saying that, let's go back to the basic setting, right, where I know the preferences. You're basically saying that there's some unobserved state of the world that influences preferences, and I'm going to try to rationalize that. A different statement of the problem could be that the guy has a random utility. I don't exactly know what the preferences of the person are moving forward, but what Bayesian updating is doing is it's giving me a class of random utilities because it's imposing some sort of restriction on the set of preferences. So is one way to interpret what you guys are doing to say that is there some isomorphism here between a class of random utility models, which are sort of parameterized by Bayesian updating, and what does that look like in some sense? Like how general is that? This is sort of the question.
I think isomorphism would be a very strong. I mean, we don't have. But yes. So going back to this kind of empirical content statement, right? Right. So So we make a stronger assumption in some sense on behavior. I think probably you can prove some result like that as long as you still put some structure on the class of random utility models. So I think
exactly right. In particular, like Bayesian updating is imposing some structure on what the preferences can be, right? But I was just wondering, because that's just an alternate way of phrasing what you guys are doing. So
so this is this is something Henrique and I've talked about a lot, and I think so first of all, I think if the theorem like that is true, that would be very cool, and I think we haven't thought about that systematically. I do think that there is value in this different perspective, in the sense that, and I want to be careful while saying this, is that somehow when we write down applied models, or we write down even in IO or something, we are happy to take stands on preferences, right? We say you like less money than more money, you want more investment like than less investment, right? Simple things like that. But somehow when we are writing down rationalizations, we are not taking any stand, or our instinct is to not take any stand. So I think that's why we started with a different perspective, which was to say, let's take some stand and see how far we get. And I think if I just look at this slide, I think what you're raising is a very good question, is that, what is a formal way to bridge these two approaches? Beyond that, I haven't thought about it systematically, but Henrique, you wanna?
Yeah, so I think maybe a good place to think about this approach that Rahul is suggesting is this paper that's been cited there, the Frick, Ijima, and Streletsky paper. Right? They talk about dynamic random utility. And they have a result that shows that, if I recall correctly, that when you think of random utility as coming from information arrival, then you have some particular structure on the random choice that can generate. So I think as long as the random utility is coming from information arrival, I think there is an isomorphism. I think it is equivalent to what we're doing. And there's some technicalities about like the finite support of the set of states, which is not very relevant. But yeah, I think it's basically the same. But I think with just pure random utility, you can have this utility moving around a lot, and so you can have other things as well.
Can I jump in here and take advantage of a break in this fascinating discussion and officially thank the speaker Rohit and the participants. So Henrique, thanks for coming. Rahul for joining us, and Jonathan had to go teaching. I'm going to stop